In part 5 of this series, I will discuss additional equipment in solar and backup systems. In part 2 of this series, we talked about solar inverters. These were grid-tied inverters. There are other types of inverters used for cars, trucks, and recreational vehicles that allow you to operate AC appliances in remote locations. These inverters convert DC from one or more batteries into an AC current. I will discuss two types, pure sine wave and modified sine wave, and how they differ. A pure sine wave inverter output looks like the black line in the image. These types are more expensive, but produce the type of electricity that appliances really want to see. This is what our grid delivers to our homes. The signal is either 60 Hz or 50 Hz, depending on whether you are located in North America or Europe. A modified sine wave looks like the square wave, which is the blue line in the image. The inverters that produce these types of square waveforms are less expensive, but produce unwanted harmonic frequencies. While most equipment will operate on this type of signal, some will not. Inductive motors will operate inefficiently and produce extra heat. I mentioned that square waveforms produce unwanted harmonic frequencies. Here's an example of what harmonics look like. Harmonics are frequencies that are multiples of the fundamental frequency or the original frequency at 50 or 60 Hz. 60 Hz harmonics would be 120, 180, 240, 300 Hz, etc. These harmonics, if not properly filtered, can be amplified in a speaker system. It is also possible to hear a high-pitched noise coming from the inverter. These are examples of pure sine wave inverters. These units will provide the sine wave output that we saw in a previous slide. You will see these in off-grid environments, as they cannot have their output connected to the grid. We reviewed solar inverters in a previous video. Solar inverters actually sync their output to be in phase with the grid frequency, but these inverters just output the frequency on their own, which will be out of phase with the grid and therefore will be damaged. They typically operate with a 12 to 24 volt input from one or more batteries, and their output power ranges from low power up to about 3 kilowatts. Let's talk about battery chargers. These types of battery chargers will charge 12 or 24 volt battery banks. They plug into an outlet and operate on house current. 12 volt chargers can deliver currents of 15 amps up to 80 amps depending on the model, while 24 volt models typically deliver up to a maximum of 40 amps. They can be used to charge batteries that can be switched on when the power goes out, or you can take the batteries to remote locations to power inverters. Even though you are charging the batteries at 12 or 24 volts, you can disconnect them and then take the fully charged batteries on the road and connect them in 12, 24, or even 48 volts. One thing to note is that the output current in these chargers is DC. The 80 amp units could make you think that the 15 amp breaker in your panel can't handle the current. Remember, the 80 amps from the charger is at 12 volts, or roughly 960 watts because P equals V times I. The 15 amp breaker is at 110 volts AC, which means that the breaker can handle 1650 watts of load. Another way to charge batteries is by using solar energy, and for this you can use what are called solar charge controllers. Solar charge controllers operate differently than solar inverters. Unlike solar inverter systems where the goal is to send AC current to the grid, the goal for solar charge controllers is to use the DC solar energy to charge 12 or 24 volt battery banks. Like the solar inverters, they control the MPPT, or mean power point tracking, to extract the most electricity from the PV panels. Not only do these units control battery charging, but also the load discharging as well. The input to most charge controllers is limited to about 30 amps of panel array current, while some can go as high as 80 amps. There are some higher power units available on the market. Here's an example of a high power solar charge controller from Outback Power. This type of unit can be used in a system to power homes in an off-grid environment. The voltage input from a much larger solar panel array than the previous examples can range from 230 to 290 volts DC. This unit can operate with either 24, 36, or 48 volt battery banks. This one provides a continuous output current of 100 amps for 5 kilowatt battery charging and is equipped for operating in large systems. When you want to switch from one AC power source to another AC power source, you can use what is called a transfer switch. Let's say that the grid goes down. You can use a transfer switch to switch from the grid to an inverter and run off battery energy until the power comes back. Transfer switches are available in manual or automatic. Some automatic ones are shown here. An automatic transfer switch can sense when the grid is down and automatically switch from grid power to the inverter power. These types of transfer switches have current limitations, typically around 30 amps, which means that you would not want to power your entire house. However, you could operate the most essential loads. Thanks for watching.